So we're going to move on to more mathematics with Ricardo Pérez-Marco and Cyril Grunspan. So Ricardo, you're the first.
Yes, thank you. Thank you very much to the organizers and to have this conference in this nice school. So I'm going to talk about joint work with Cyril, and he's going to make the second part of the talk. This is about rogue mining strategies, so essentially block withholding strategies. So I will need to describe first the economic incentive of these rogue strategies. And well, this is about work that we have been doing in the last year. So first I will discuss the model of profitability, and then Cyril will talk about the mathematical techniques to get the formulas for profitability. And we will discuss the main mathematical tools to deal with these problems. So we are mathematicians, so we have a slightly different culture of presenting things than computers in computer science. So we'll focus on proving theorems and doing some kind of more mathematical analysis. So indeed, the first paper was about 1 year ago, where we clear out what is the profitability model that was kind of lacking in the literature. So I'm going to explain what is the difference of what we did and what we existed before. And then we apply this profitability model and the new tools which use Martingale theory to different selfish mining strategies that were around in the literature, mostly with numerical studies, like stubborn mining and trailing mining. All of this for Bitcoin, okay? And then we discovered that there is a very direct approach, which is not completely general, but gives the old results with Markov chain models, which we can get. This gives the long-term profitability. So we can get this directly using combinatorics, using Catalan numbers and Dyck words. And so we apply this to Ethereum also. And the last paper is just out a few days ago. It's about selfish mining in Ethereum using these tools. Okay, so first I want to discuss the profitability model, which I think is of interest to everybody, to economists and computer science and everyone, because we need to understand what it means to be profitable. You know, usually in the balance you look at the profit and loss, but what is important is the profit and loss by unit of time. So profit and loss is the revenue minus the cost, but what is important when you have an advantage strategy is not that you have a positive profit and loss, but how long it takes to get this profit and loss. So your monthly salary that is important is not your abstract salary, it's how often you get it. Now, these time considerations are, I mean, the new aspect that we are considering, which is fundamental to evaluate the profitability. In any business, what matters is the profit and loss by unit of time. So you look at the revenue at time t, and you subtract the cost, and then you divide by t. And if you have this, if this limit exists, you will get the long-time revenue, okay? And this is what is important for a strategy, to have something profitable. Now, when you find out an advantage strategy, what you do is you repeat it often and often. So there is what we call a repetition game, okay? And this is very common in gambling. You find a way to make money on the roulette, and you repeat this often and often, and what you want to estimate is how much you make per day, per month, etc. Now, well, this is very common in gambling, and for instance, if you look at poker players, they look at the wage they make, hourly wage, okay? This is why it's more profitable to play online than to play in a casino. You have many more rounds per time, I mean, okay? Now, this is not game theory, okay? It's called repetition game, and this terminology comes from gambling, but has nothing to do with game theory in the sense that it's not a game theory setting. It's just a game that you play and you repeat. So you can just call it repetition strategy, all right? Now, so you repeat over and over these cycles of attacks. And so I'm not just discussing the specifics of selfish mining. We will come back to that later. But you just have a strategy and you repeat this and you have cycles where you return to the initial state. Now, we can consider 3 random variables for each cycle. So a random variable means that this is a variable that depends on the cycle you are executing, can take longer or shorter time, but it has a distribution. So you have the revenue per cycle, you have the cost per cycle, and you have the time per cycle, the time it takes to complete the cycle of attack and return to the initial state. Now, it's just an application of the law of large numbers, that the profit and loss, the long-term profit and loss, is just these expectations of R minus the expectation of C divided by expectation of T. Okay, so this is just pretty simple indeed, just to apply the law of large numbers to get this revenue and for the profit and loss in the long run. Now, what is important now to understand is that we are not going to estimate the cost of a strategy. This is complex to estimate the cost of mining, but we are going to compare different mining strategies. All right? So what is important is this, first, this revenue ratio. So the revenue, the expectation of the revenue divided by the expectation of time, and the cost ratio, the expectation of cost per cycle divided by the expectation of time. And what is clear is that if we have 2 strategies with the same cost, all right, the same epsilons, then in order to compare the profitability, you only need to compare the revenue ratio, okay? So you don't need to know the cost. If you know that the costs are equal, you don't need to know, to dig into what are the costs of mining, buying hardware, paying energy, etc. And this is what happens with mining. All right, so what is the block withholding strategies? So according to the usual protocols, the Bitcoin protocol and Ethereum protocol, a miner should release a block that has validated. She should not keep it, okay? Of course, all these protocol rules are not enforceable. The only warranty that it's working is that because the stability of the protocol, which means that the rules of the protocol are in line with the individual interest. Now, these block withholding strategies consist in, for a miner to mine a block and keep it secret, and continuing building a blockchain on top of this secret block and his secret fork, and release this fork at the appropriate moment to invalidate the honest blocks, okay? This is the general principle of these block withholding strategies, which goes against the protocol, okay? And the point is that what people discover is that this can be profitable. So the Bitcoin protocol is not stable in this sense. So there are different block withholding strategies. You can have set different algorithms to release the blocks at the appropriate moment. There are some more risky than others, some more aggressive than others, some that look for hurting the honest miners more often or increasing your profit. So there are different types of block withholding strategies. And a key observation is that all these block withholding strategies have exactly the same cost as honest mining if you run your machine full time. If you think about it, you are just deciding when to release the blocks, but the cost, the operation costs are the same. The salary you pay to people in the mining business, the hardware you buy, the energy you pay are the same, all right? So this is the key observation that allows you to compare different strategies, because then, as I said before, you only need to pay attention to the revenue ratio. So some important observations is that as a corollary of this, so the comparison of profitability is independent of the current exchange rate of the coin you are mining, all right? It doesn't matter. You know, it is, of course, the cost will have to implement, you know, volatility of the markets, etc., but you don't care. They are the same in both strategies, so you just don't care about it. The cost depends on external factors like energy, hardware cost, etc. But this is independent of the strategy. So we don't need to look at this in order to compare strategies. So this is a nice thing because then we can build a purely mathematical theory. Now, what is the profitability of bulk withholding strategies? So it's profitable in the long run if this revenue ratio gamma is larger than the revenue ratio of the honest mining. And an important fact that we see this as important is that indeed we have a stability theorem in Bitcoin. So without a difficulty adjustment, so this is an important condition here, there is no bulk withholding strategy that is more profitable than honest mining. And this is indeed a non-trivial theorem. You need to prove this theorem some Martingale theory. It's the same as to prove that in roulette, when you go to the casino, there is no profitable martingale. You know, this type of strategy that people bet, and if they lose, they double their bet, etc. All right? So this is the same type of mathematical result. You cannot prove it without some mathematical technology like martingale. Okay? And you know, the bad thing about this is that with difficulty adjustment, this is not true, okay? So even if this is what the intention of the creators of Bitcoin and the cryptocurrencies, to prove it is another business. Okay, it comes as no surprise, you expect this to be true, but indeed it is not true because it's only true without a difficulty adjustment, okay? So we have this theorem, which is quite satisfactory because it shows that the protocol is well built. Now, the proof deals with martingale techniques and dupe stopping times. So you need to use some particular tools that were not available before our papers. So before, what was available was just a corollary before talking about the precedents. A corollary is that this block withholding strategies are all an attack on the difficulty adjustment. Okay? So it's not really an attack on the protocol. It's just specifically about the difficulty adjustment algorithm that is attacked. So the main problem we have in Bitcoin and Ethereum is that the difficulty adjustment does not account properly of orphan blocks. Well, this is some kind of taken care by the new difficulty adjustment algorithm in Ethereum, but not totally. And the solution that we propose to this is that you can modify indeed the difficulty adjustment formula, taking into account orphan blocks. Anyway, the previous Markov model, you cannot get this type of result with the previous Markov model, which was based on the following. So, well, the main parameters of the problem is the relative hash rate of the attacker that you assume that is less than 1/2, otherwise you can just control the network. And the connectivity of the attacker, which is the probability that when you release a block, it's the fraction of honest miners joining your fork, okay? Now, these are the main parameters, and the chain state is essentially defined with the length of the honest chain and the length of your fork, your secret fork. Okay, this defines a Markov state, and then in the classical study, you look at the transition probabilities. So this is indeed fine to compute the relative proportion of blocks that you will end up mining. Now, the problem with the Markov chain model is that when you pass from one state to another, it doesn't tell you, and you cannot know how long it takes. And this is key for the profitability, for the time profitability. All right? Now, so since we don't have this information, for example, you cannot prove this stability theorem with this model. And it's impossible to answer some basic questions. Like, for instance, when you engage on a rogue strategy like segface mining, you know that you need to wait for the difficulty adjustment, the difficulty to go down to become profitable. But how long it takes? Because you are losing money at the beginning, okay? So then you need to catch up. So how long it takes for the strategy to become profitable? And you can answer with the Martingale model how long it takes. For example, if you, well, okay, just to explain quickly, the technique with martingales, what you observe is that the number of blocks validated at time t by the honest miners and the rogue miners, I call this nt and n prime t. So these are Poisson processes with parameters alpha and alpha prime, and you assume that alpha prime is less than alpha, which corresponds to q less than 1/2. Now, so this means that the probability for having n of t equal n given by Poisson distributions. And now we have a theorem or a lemma that we use, is that we call these Poisson races. So if you have two independent Poisson processes and you start with 0 at t equals 0, then you define the stopping time is the time where n of t is larger, is the first time that is larger than n prime. Okay, this is mathematically well-defined stopping time. And this is finite almost surely, so the honest miner will catch up and integrable. Now, also using this stopping time theorem, you can compute the expectations of tau, and which is the stopping time, as well as the expectations of n and n prime. All right. So this gives you the key in order to compute the profitability ratio, the expectation of t. All right. Now, for example, what I was telling before is that if you start with q equal 10% and gamma equal 90%, it takes about 10 weeks for a selfish mining to become profitable. Okay, so it's not exactly very profitable at the beginning, and many things can change in 10 weeks. So, okay, so as I said, it's impossible to obtain this result with the Markov chain model. And now, if you want to get only the long time profitability, we discover a new technique which is very direct and that Cyril is going to talk about it. So this uses Dyck word, Catalan numbers, and Catalan distribution. So I let you continue with this new combinatorial technique.
Yeah. So basically, a Dyck word built on the alphabet SH of length n is nothing but a string containing ns and nh, and such that no initial segment of the string has more h than s. Dyck words are really well-known object in combinatorics and mathematics. So the number of Dyck words are denoted by Cn, the Catalan numbers. We denote by C of x the generating series of the Catalan numbers, and by D the space of all Dyck words. The generating series can be obtained via such equations. The first one can be derived using basic random walks theory, and so it's just another interpretation of the equation giving C of x. So selfish mining and Dyck words. We describe an attack cycle of the selfish mining strategy with the help of the chronological sequence of discoveries S and H. S for selfish, H for honest. For example, SS, SHSHH means that the selfish miner has mined 3 blocks in a row, then the honest miner has mined 1, then again the selfish miner, and then at the end the honest miners have mined 2 blocks. And so, according to the rule of the selfish miner strategy, the attacker release all his fork, all his secret fork, and the attack cycle takes end. The link between selfish mining and Dyck words is given by this theorem. Basically, the substring in the middle of an attack cycle is a Dyck word, substring in red here. So this allows us very quickly to compute, the average, the distribution of the number of official blocks added to the official blockchain at the end of an attack cycle. It is the corollary given here. And it gives very quickly also the number of blocks mined by the attacker at the end of an attack cycle. L and Z are more or less equal. They are equal when L is greater than 3. So once you have the distribution of L and Z, you just compute the expectation of L and Z. This is the expectation gives you the expectation of L, expectation of Z, and if you compute both of them and take the ratio, then you get the revenue ratio. Indeed, when dealing with Bitcoin, the duration time of an attack cycle is just proportional to the number, to the mean number of official blocks added to the official blockchain. And since you have the distribution of L and Z, you compute the expectation, you compute the ratio, and then you give this, you obtain this way a two-line proofs of the formula given by Eyal and Cyril in their paper. Okay, we can consider also other classical strategies using the same tools. They are called lead stubborn mining or equal fork stubborn mining. They are less conservative block withholding strategies. The same techniques give you directly the revenue ratio of the strategies using a little bit of combinatorics of Catalan numbers. And then you can picture the region of Q and gamma according to which strategy is the best. And such a graph has been obtained numerically by the author, Meyer and his collaborators. But here you have the closed form formula. Okay, now we turn to Ethereum. Ethereum has adopted a totally different reward system and a difficulty adjustment algorithm. This is due to the fact that the interblock time, the duration of the interblock time in Ethereum is much reduced, around 15 seconds approximately. So it gives potentially rise to a huge creation of orphan blocks that are taken into account in the rule to decide between two blockchains according to a variation of the Ghost protocol. And to incentivize miners to signal orphan blocks, uncles are rewarded. Uncles get reward as well as a nephew that signal uncles. By definition, an uncle is a stale block whose parents belong to the official blockchain and that are signaled referred by a nephew. A nephew is an official block belonging to the official blockchain. And there is a law stating that the distance between the nephew and the uncle must be less than 6. And also a nephew cannot refer more than 2 uncles. Also, another important point is that the difficulty adjustment in Ethereum takes into account the prediction of uncles, and also this you don't need to wait for 2016 blocks before the difficulty go down. Okay, because the difficulty adjustment in Ethereum is made continuously. Okay, so potentially it is very dangerous for the protocol. Let's see. So the protocol takes uncle and nephew into account. Yes, so according to the different reward system, there is just one selfish mining strategy in Bitcoin, but there are several selfish mining strategies in Ethereum. Indeed, the attacker can keep secret his fork until the very last moment of the attack cycle and release all his fork, creating a big reorganization of the official blockchain. Another possibility is simply to release slowly his fork each time the honest miners find a block. So this way you create a lot of artificial competitions between the honest miners and the attacker, and you create a lot of uncles that can be referred by the attacker. increasing potentially his revenue. So, first strategy is this one. You broadcast slowly, one block by one block, your fork. Each time the honest miners mine a block, and you signal all the possible uncles. This is SM1, and this is a strategy that had been considered by Chen Feng and Jianyu Niu recently in a recent paper. So the goal, finally, of this strategy is simply to maximize the revenue. Another possible selfish mining strategy in Ethereum, you just you signal all uncles, but you keep secret as much as possible your fork, releasing it only at the very last moment of your attack cycle. So you have few uncles, but you refer them. And last possibility, you do not even refer an uncle. You refer no uncle, okay? And you avoid competitions. So this way, you maximize the impact on the difficulty adjustment. Okay? Now we used the same tools as before, using Dyck words, and we get closed form formula again. So you can find the closed form formula in our papers. So what we obtain is the following. First theorem, the first strategy is always less profitable than the second one. Means that you have never ever you should enter into competition with the honest miners when you are an attacker. Okay. And even when you have more than 30% of the relative hash rate of the network, then you don't even you can simply ignore uncles. And here is the graph which pictures the region of Q and gamma according to which strategy is the best. So so there is a HM, honest mining strategy, in yellow SM2A, so the second minimum belligerence and the attacker refer uncles, and at the right, the strategy where the attacker simply ignore uncles and keep secret his fork as much as possible. So we can get also the threshold profitability and compare the threshold profitability of Bitcoin with Ethereum. And we see that Ethereum is much resilient than Bitcoin for low relative hash rate, but it has the opposite effect when the relative hash rate is greater than 25%. Yes, now I'm here at the conclusion of this talk. So the important thing is that we have used a new concept, a key concept, which is, that we have called the revenue ratio. The revenue ratio is a correct objective function to compare profitabilities of mining strategy. It is not the relative revenue that you can find in other papers. And this revenue ratio allows us to use a combinatorics approach to compute it and to compare the profitabilities of different strategies. And this way we can get quickly closed form formulas. We see that the study in Ethereum confirms that selfish mining is an attack to the difficulty adjustment, the same result as in Bitcoin. Ethereum is more resilient than Bitcoin for small hash rates. And Ethereum's continuous difficulty adjustment favors selfish mining. Yes, because the difficulty adjustment is made continuously in the network. So once the attack is profitable, it is immediately profitable. You don't need to wait for several weeks as we have computed for Bitcoin. It's almost immediate. So the effect is potentially devastating in Ethereum. So Ethereum has adopted a better, much better difficulty adjustment than, compared to Bitcoin because it considers uncles. But it has also adopted the biased reward systems, which favors selfish minings. And the fact is that the best strategy when Q is greater than 25% is simply to avoid competitions and to ignore any uncles.
Thank you.
Thank you.
So just something that wasn't 100% clear is the revenue and the cost is measured in Bitcoin or in Ethereum. The question is, if you measured the, how much more money one would make compared to the others, and why would that be important? Because there is the case where if I make the rest of the network slower, then there are less blocks produced, and so even one of my Bitcoins has more value. Did you consider this or not?
No, we have not. We cannot compare the two costs of mining. We did not compare the cost of Ethereum with the cost of Bitcoin. No, but the fact is that according to the threshold of profitabilities, we see that when the relative hash rate of the attacker is less than, let's say, around 25%, then for the attack to be profitable, the attacker needs to be very well connected. The gamma needs to be very wide. Whereas, when the relative hash rate of the attacker is greater than 25%, it has a opposite effect. But it doesn't mean that it is more profitable to mine or to selfish mine in Ethereum or in Bitcoin. You see?
Okay, thank you.